Okay, so let's resume. So let's actually start with let's take a tangent and talk about some software. Okay, so on the syllabus page there are a couple of software links. Okay, so there's something called PGMPy. There are many softwares for working with graphical models, but this is just to get some intuition, and there's some notebooks in that that particular package. You can install it on Conda or PyPy. So there's some examples of how to work with graphical models, conditional independence, making inference. So they have all the like belief propagation is implemented in that. And the next PyMC3 is for Markov chain Monte Carlo, MCMC methods. So for that also there's a package called PyMC3. Actually, let's look at before we get into the topic of sampling, let's look at the Monte Hall problem. So how many of you have heard of the Monte Hall problem? Monte Hall problem. What is it about? Yeah. So the Monte Hall problem is as follows. So let's say you're in a game show and you have 3 doors and you just need to pick a door, and that's it. So you pick a door, and the host will tell you something, okay, and based on that you also have the option of changing the door you picked before, and hopefully there's reward behind the door, then you get the reward. Okay, so a priori it's not, so you don't know where the reward is, so reward is only behind one of the doors. So let's say, so you just randomly toss and pick one of the doors. Okay, now the host is going to reveal some information. In fact, what the host is going to do is open one of the doors where there is no reward. Okay, the host is doing something which is open a door which has no reward, and given that information, the question is, the door you initially picked is still closed, and there's one more door which was not opened. The question is, do you want to switch to the door which was not opened but the one that you did not pick, or can you still keep the door that you picked? Okay, so what do you guys think?
Change.
Yeah, should you change, or why is that?
Because I saw the movie Blackjack.
Blackjack has so the movie has a Monte Hall problem. Okay.
It's because the probability equal to 66% because they're looking at 2 doors as one instead of your door as one.
Yeah, so okay, there are several explanations of why you should switch. Okay, switching is apparently a better strategy, but a priori it doesn't make sense, right? Like why should I switch given that the host said, given that the host only opened a door which has no reward anyway. So the reward is between the other 2 doors. Why should I switch? Yeah, it's a Monte Hall problem. One way to think about it is through the lens of graphical models. Okay, so you don't really need graphical models. You just need the graph. Okay, which is or the dependency between random variables. So what are the random variables? One random variable is what I choose. Okay, I'll choose door 1 or 2 or 3. Okay, the second random variable is where is the reward. Okay, that is also random, right? It could be in first door, second door, or third door, irrespective of what my random variable is. Okay, those are the 2 random variables. Okay, those 2 random variables together influence the host's decision to open a door or not. Okay, so the host has a random variable. Think of that as a random variable. Host decision to open some door. That depends on where the true reward is. That could be random and depends on my choice of which door I pick. Okay, so there are 3 random variables here. The host's random variable is dependent on the other 2 random variables, and that's it. Given that graph, now you can compute all sorts of marginals, conditionals, and stuff like that. Okay, conditionals only because now you have an evidence that the host opened certain door. Okay, so condition on that and condition on that. What is the probability that the door you picked has a reward? What is the probability that the door you did not pick has a reward, and so on? There you will see that door, if you switch, then that option has higher probability of having a reward. Okay, so that information is in this PGMPy package. there's a notebook. Actually, this is a notebook. The notebook is called Examples and Monte Hall Problem. Okay, so it just shows you what the random variables are: probability of C, you choosing something, probability of the price behind something, and yeah, who's talking? Okay, so and the probability of host choosing something given that the price is somewhere and you said something. Okay, so this is the dependency. Given this dependency graph, then you can just compute marginal probability of which door you should have chosen given the host evidence. Okay, okay, is that clear? Or I think you should spend some time just going through this example and the concepts that we learned in the last class and this class, so that you don't have to think of some. I mean, there are other ways to think about this problem where you think of probability spaces and two doors into one and all that stuff, but this is I would say a cleaner. I would say relatively cleaner, given that we have spent 6 hours now on this topic. Might as well use the technique, right? Okay, so yeah, so PyMC is what the other package I was talking about, which is relevant to this section, this part of the lecture. It's a package. There are other packages also, but it's a package to do basically Markov chain Monte Carlo sampling to do inference. Okay, so as I said, if you do if you're a Bayesian, you'll always maintain posterior distributions over objects of interest, and if you do that, then you want to infer something like use that posterior distribution to make a prediction. You will need to do inference in the sense that you will need to marginalize out the random variable, which is your belief on what the true model is. Okay, so now the model itself is a random variable. You need to average it out basically. So that therefore, if you need to do marginalization, MCMC are basically MCMC or belief propagation will help you. Okay. With that, let's actually get to MCMC. So how many of you have seen Gibbs sampling before? Any sort of sampling? This is a trick question because we saw sampling, right? We saw sampling using GANs and VAEs, right? So, but what about Gibbs sampling? In 575, you've not seen Gibbs sampling? So, did you not see Gibbs sampling? You did. Okay. Okay. So there was some motivation to sampling that I gave before, but the motivation for today's lecture is the same, right? Sampling for inference. That's what we want to do. We want to compute expectations. We want to compute marginal probabilities. We want to compute conditional probabilities. Okay, that's the goal. And unlike sampling, the previous methods, especially just belief propagation, that's the key method that we saw, is an exact method. Okay, in the sense that if it's a tree, then it will give you the exact answer. Okay, whereas in sampling, it's all about approximations. Okay, we want to get some actual observations from some distributions and hopefully use averages and so on, and that will be an approximation to things that you want to actually compute. So you are really not going to do integration or the summation. You'll actually get some numbers, take an average, and that hopefully that average is close to the number that you care about, like an expectation. Okay. There are many methods, so it's a huge basket of techniques for sampling, and we saw GANs and VAEs a few lectures ago, 3-4 lectures ago. Today we're going to look at a sequence of essentially 4 techniques. Okay, from simplest to a little bit more complex. Okay, the first cluster is Monte Carlo methods. It includes just what is Monte Carlo averaging and importance sampling. Okay, and the second key thing in that is called rejection sampling. Okay, so we'll say, why do we need all these? Why am I giving you this sequence of methods? The second set is just to give, the first set is to show you if you had access to the distribution itself, then you can just get the samples from the distribution. Okay, in the sense that if you know P of X, in some form, let's say it's a normal distribution, then you can just get samples. So numpy.random.random, right? But you'll see that there will be different levels of access to a distribution, and given that different types of access to a distribution, you can sample. Okay, that's the first cluster of MC averaging and importance sampling and rejection sampling. The second cluster is just 2 ways to sample from joint distributions, which involve what is called a Markov chain. Okay, so I'm going to describe what a Markov chain is when I get there. Okay, so the first cluster is easy. It's a warm up. So let's relatively easy. So let's do. So what is Monte Carlo averaging? Okay, it's a very simple idea. So if, let's say we want to find the expectation of f of x. Okay, so let's say x is a random variable. I just want to find expectation of a function of that random variable. Okay, so how do I do that? I just do this integration or a summation, right? So it's just the integration of f of x times p of x dx, right? Now, or summation like this. Now, what is the Monte Carlo averaging idea? If you can have access to the distribution, if you can get samples from the distribution, then I don't have to worry about some complicated integration. Okay, because remember, even normal distribution has some e to the power minus something. So integration of f of x, let's say f of x is like 1 by square root x, okay, times e to the power minus something. It's a messy integration, right? Generally, because normal distribution is a very messy probability density function expression. So what you could do is maybe just get samples. Maybe you get capital L number of samples from the distribution p of x, and then just take a average, okay, uniform average, which means that you just average the function value at these samples, multiply it with sum the sample functions of the samples divided by L. Okay, so that would be and the claim is that as long as you get the samples from the true distribution, first of all, of course, the sampling is the expectation of this estimator f hat is exactly equal to the expectation of f. Okay, that's just because it's an unbiased sample. You're getting the sample from the distribution that you care about. So expectation of f hat is going to be expectation of f, and f hat itself is going to be close to, and f hat itself is going to be close to its expectation. Okay. Okay. Two things. One is if I get samples, too many samples, f hat is going to be close to its expectation. Okay, and its expectation is actually equal to just the expectation of f, which is what we cared about. Okay, so all I'm saying is if you sample an average, then it's good, it's fine. Okay, if you have access to the distribution, in this case, you need this this thing p of sample should be drawn from p of x that you care about. Okay, is that fine? It's a warm up for what is Monte Carlo averaging. Okay, any questions? Okay, next. Oh wait, this expectation here?
Expectation of f hat is a value, right?
F hat is an estimate. F hat is an estimate. It's a function of random variables. Yeah, it's a function of random variables.
Expectation of the
function of a random variable. Yes. So think of x1 to xl as random variables, and f hat is a function of those random variables.
Sure. So I'm saying that f hat is eventually going to be a value, and the expectation of the value equals to the value itself.
Yeah, if you get different samples, you get different f hats, right? So there's a distribution of f hats. Take its expectation. Yeah.
I see.
Is that same confusion there for other people?
What is the estimate expectation or is it a function?
No, f hat is just defined here, right? So this is f hat. It's an estimate. So f hat is a number that you can get if you had L samples here, but it's random, right? If I get different L samples, I get different thing else. So I'm saying now, since it's random, take an average, take its expectation. I'm just saying that it's an unbiased estimate because its expectation is expectation of expectation of f. So this is unbiasedness. Okay, and it's a specific term used in statistics. An estimator is unbiased if its expectation is the parameter that you care about. There's nothing central limit here happening. Yeah, so the second thing that I wrote here has some law of large numbers involved. Yes, not central limit theorem, but just law of large numbers here. It's slightly different. Okay, so central limit theorem, for those, because she threw the word here, is just a quantitative version of law of large numbers. So law of large numbers is a basket of phenomena, or you can, you have strong law of large numbers, weak law of large numbers, and there's some quantitative versions. Central limit theorem is think of it as some variation of that. How is the underlined one different from? So how is this different from this?
How is this Monte Carlo averaging different from central limit?
No, central limit theorem is talking about your distribution of your sampling distribution being normal. I think normal. There's nothing normal distribution here. Yeah. So there's something called a population distribution and a sampling distribution. A sampling distribution is going to be normal. Okay. But let's not go into that detail now. We can discuss it offline. So that's Monte Carlo averaging. We're going to improve that by importance sampling. Okay. Importance sampling is just a way to reduce some property of that previous averaging technique. Okay. Previously we were just getting samples, average it. Okay. Now what we're going to do is actually do something else. We're going to draw from a different distribution. Draw samples from a different distribution. Okay. Completely different, but on the same support, of course, right? If X is a discrete random variable 10 values, and hopefully the other one is also discrete random variable 10 values. Okay. So we'll get samples from Q of Z, and then we'll average. Okay. And it's kind of clear how we can average. So if this is what we cared about, integration of f of x, p of x, f of z, p of z, dz, right? So that was the expectation of f. I changed from x to z here. I just multiply and divide by q of z, right? Q of z is a distribution. So now I can think of this as my new function. Sorry, without that part. This is a new function, and there's a q of z outside. Oh my god, it's messy, but all I'm saying is you think of this f times p by q as a new function, and then you have the usual q distribution on the. Okay, maybe I should erase this, undo this. Yeah. So all I'm saying is just think of this as a new function, right? And then you have the same problem as before. If I get samples from q, then I can just take the average of the squared thing over here, right? It's the same squared thing. It's just the samples are from q, okay? And then I am taking average of p by q times f of the samples, okay? Nothing has changed except the function has now become messy. So I wanted to find an expectation with respect to p, but I got samples from q, and still I can compute the expectation with respect to p. Okay, I just did this correction. There's a correction which is this term in the front of f. Okay, so which means that I don't even need access to sampling from p at all. So from the previous slide, I needed samples from p itself. Here I need samples from some other distribution. Okay, I don't need samples from phi. I just need to evaluate what is the mass at a given sample. So I need to just evaluate p of x. I don't need a sample from p of x, and I can still compute the average. Right? Yeah.
So does the distribution need to be similar? Q and Q?
So whenever p is non-zero, q has to be non-zero. Okay. Good question. So his question is whether p and q have to be similar in some sense. Yeah. Whenever p is non-zero, q has to be non-zero, because if q is 0 and p is non-zero, then you're never going to get samples from there. Then it's not going to match. Okay. So that's it. That's importance sampling. And there's another variation, which is okay. So I don't have time. Okay, I don't have time about this, but it's just saying that if you cannot evaluate p of x itself, so sometimes you don't know the distribution. So think of the undirected graphical model. So let's not go into the details of the slide actually. So in this slide itself, what I'm saying is that you had to find p of z, right? P of zl. So you want to compute p of zl because it's a part of that summation, right? What if, think of the undirected graphical model case. You had the 1 by z times some factors, right? What if I can't compute the z? Okay, that z is called the partition function. It has summations, bunch of summations involved. Maybe it's too expensive to compute this z thing, okay? But it's easy to evaluate the factors, because there's no summation with the factors, right? So which means that I don't know p of zl, for example, but I only know something proportional to p of zl. Okay, even that can be fixed. So you don't need even access to the normalized. You don't need access to the distribution function itself. You just need some scaled up version. That's good enough. Okay, it's a minor point. All I'm saying is you don't need a normalized p of z to get to this type of expectation estimation. Okay. The detail is same, but let me skip that. Okay, so that was importance sampling and just Monte Carlo averaging. The next item is rejection sampling. Okay, so what is rejection sampling? It's slightly different. But what is the goal? The goal is still to find. So the goal is now, let's forget about expectation. The goal is now just to get samples from P of x, a target distribution P of x. I care about the distribution. I want to get samples from it. Okay, whether I use the samples for expectation or not, that's later. I mean, in the previous slides we saw that we were using it for expectation, but now I just want to get samples from P of x. Okay, so rejection sampling is the idea that you want to get samples from P of x, but I will give you, I'll actually generate samples from another distribution Q of, in this case Q of x, okay, and do some sort of an accept rejection mechanism. Okay, so P of x is hard to sample from, most potentially because it's kind of maybe non-linear, it's kind of messy, multiple modes, maybe it's not easy to describe, maybe it's a posterior of some Bayesian computation, maybe it's hard to describe. Okay, then what you do is maybe you can somehow sample from an easier distribution like a normal distribution, and still and have an additional accept reject mechanism such that as if you're getting samples from P of x itself. Okay, and we'll look at this picture in one dimension. So what is the procedure? Okay, the procedure is a two-step procedure to get a sample. First you get a sample from this proposal distribution Q of z, so Q of x. Okay, and it has to have a special property that Q of x is always going to be greater than or equal to P of x. Okay, but that is not true in the sense if both if Q of x and P of x are probability density functions, then one cannot completely be greater than or equal to the other. Okay, because they need to sum to 1. Yeah, as you were pointing out, so it has to sum to 1. So we are allowing for a slack. So just multiply with Q of x with some number k, let's say 2 or 3 or something, as long as it's completely or supersedes the P of x. So the red curve is P of x in this one-dimensional example, from which I want to get samples from, and the blue curve is the usual Gaussian distribution. Okay, from which I can easily get samples from. That's assumed to be true. Okay, so what we do is first get the sample from the Gaussian distribution. Okay, let's call that the random variable z0. Maybe it takes some value z0. Let's say little z0. Then we sample a uniform random variable, sample a value from the uniform distribution between 0 and q of that z0 that we got from the previous step. Okay, so in terms of imagery, first you get the z0, okay, from the domain, so on the z0. Then on this line over here, this black line over here, you get a sample uniformly. Maybe it falls in the shaded gray region, or maybe it falls in the white region. If it falls in the white region, you accept that value z0 as you accept that value z0. If it doesn't fall in the white region, you reject that value. Okay, all these accepted random variables are going to be samples from P of x. Okay, that's the procedural intuition. I didn't prove it to you that yeah, you get the sample from that. Any questions about the procedure? This is called rejection sampling. Okay. Yeah, and the intuition is somehow that basically, if you want some intuition, just think of it as like let's say there are a bunch of blocks here. So let's say this is the distribution. Okay, this is the distribution. Let's say this is Q and P is this that Q, K times Q, and P is this distribution, maybe this shaded distribution. The intuition is that to get a sample from P, which is the shaded red color region, first, if you can get an easy sample from the Q distribution, then it's as good as saying if you can get a sample from Q, maybe the sample is one of these values on the x-axis. Then you just have to uniformly pick, when you get a sample from Q, it's going to just pick that coordinate where Q is kind of high, right, intuitively, and it will not pick coordinates where Q is not high. But whichever one it picks, if you just look at that line, then you just want to cover the area corresponding to P and drop the area corresponding to Q. Okay, that you can uniformly. So you have two regions, and you just want to pick the region corresponding to P. Okay, that's very intuitive, I guess, a very rough explanation of why this works. Okay, so that's rejection sampling. So that's a warm up. Yeah, let's not worry about probability of acceptance. It turns out the probability of acceptance is 1 by k. So the worst k is this k. If k is, let's say, 10, then the probability of me accepting is 1 by 10, something like that. Okay, so you don't want to have bad k values or this multiplier here. Okay, but these are design choices when you actually implement rejection sampling. Okay, anyway, actually there's more information about this. So this is an example of what happens to k. Okay, k is something like this. In high dimensions it's explodes or explodes essentially, and so you get it's impractical to do rejection sampling in high dimensions. Okay, but the details is not very important. I'm just saying that k is inversely related to dimension. Sorry, k and dimension kind of kill the utility of this model. Sorry. So larger the k, larger the dimension, the worse the method is. Okay. But now let's get to the interesting or more advanced sampling techniques. Okay. The first technique that we're going to look at now is belongs to the class of Markov chain Monte Carlo techniques. Okay. It's called Gibbs sampling. So actually I teach Gibbs sampling in 575. So none of you have taken that. Okay. Okay, so to understand Gibbs sampling, I want to define an intermediate quantity called the Markov blanket. Okay, why do I want to define that? Just to, and you will see this Markov blanket business. It's going to be useful when you look at when we tie this to graphical models in the next few slides. Okay, so what is Gibbs sampling? So the objective is the same: find a sample from a target distribution P of X. Okay, it's a joint distribution. So think of 100 variables in X or whatever. What we're going to do is generate a sequence of samples. We'll generate this sequence by, so let's say P of X is P of X1, X2, X3. Let's say there are only three variables. Then Gibbs sampling, what it does is it just wants access to these objects, these conditional probabilities, probability of X1 given X2, X3, probability of X2 given X1, X3, and probability of X3 given X1, X2. Okay. Gibbs sampling needs access to these three guys. Okay. If you ideally want to sample from the joint distribution, it's complicated. Can you give me access to these conditional probabilities? If you can, as in, can you give me samples from these one-dimensional univariate conditional probabilities? If you can, then what Gibbs sampling does is it samples one coordinate at a time. Okay. It samples the first coordinate given some previous values, for example, given some previous values of the other two coordinates, then samples the second coordinate given the values of the previously sampled coordinate and maybe some stale information, and then samples the third coordinate given the previous two values. Okay, so it does some sampling coordinate by coordinate, and I'll revisit this point, but all I'm saying is it generates this sequence and there is dependency across samples. Okay, the samples are dependent, they're not independent samples. Okay. So that's Gibbs sampling, and Markov blanket is, okay, so I wanted to introduce Markov blanket on this slide, which is that let's pick a node. So think of a directed acyclic graph. This is a directed acyclic graph. If you focus on a node X4, its Markov blanket is all its parents, all its children, and it's all its children's other parents. Okay, three things: parents, children, children's other parents. Okay, so in this case X6 is the child, X3 is the parent, and X5 is the other parent of the child. Okay, so those are so why am I defining Markov blanket? You'll see that these conditional probabilities are just going to depend on variables related to the Markov blanket, and everything else is going to kind of somehow not pay is not important. Okay, let's actually go through an example. So this is a directed acyclic graph with several variables, right? 7, 8, 9 variables. Okay, so let's say we want to find a sample from P of W. Okay, so we want a sample of W. Okay, but W is connected to a bunch of other random variables. Okay, so how do we get the sample? So we can get a sample for W by looking at its Yeah, by looking at its, so if you want to get a sample for W, okay, so W can depend on, as I said, in the Gibbs sampling, you just won't need access to a probability of sampling a coordinate given all other coordinates, okay. So I want to get a sample for, so actually I want to get a sample for not just W, sorry, probability of W given all other coordinates, okay. All I'm saying is that given all other coordinates, you can drop the variables which are not in the Markov blanket. So the Markov blanket for cold weather W is just going to be its children, okay. There's no parent, there's no parent of its children, okay. So probability of finding given sampling from W given its parents is just the probability of sampling W given the two children, okay, flu and cold in this example, right. So how do we do that? So remember, for directed probabilistic graphical model, we just have these factors which are the variable given its parents, right, which means that you can express that term, factor term, as a table, right. The table will have, given the parents values, what all, maybe I can take 2-3 values, then what is the probability of that, okay. It's called a conditional probability table, right. So for example, for example, let's say the table for W itself is just, let's say W is binary, so it's taking values, with probability of W is 0.4 and 0.6, okay. But we don't want probability of W, we want, as I said in Gibbs sampling, we want probability of a coordinate given every other coordinate, okay. We just don't want the independent probability of W, okay. So if I have been given a directed probabilistic graphical model, then I'll have a table for every factor, okay. That's true for both directed and undirected anyway. So table for W, table for F and W, because this is for probability of flu given W, right. That's one of the factors in the TPGM, and this is going to be probability of C given C given W. I think this is not correct here. Anyway, okay, there are 3 tables, okay. So actually, okay, so we removed some variables because of the Markov blanket idea. Then what we're going to do is apply Bayes rule, actually. So probability of W given F and C is probability of F given W times probability of C given W times probability of W is not equal to, sorry, there's a proportionality, yeah. So I think the last one is incorrect, right? Yeah, I want probability of C given W. Yeah. Oh, you're saying this is
Everything else is correct except for F.
Yeah, right. Anyway, so all I'm saying is you wanted to compute this by Bayes rule. I mean, the tables you actually have from the graphical model is only these tables. Children, I mean the variable given its parents, okay. So all we did is just use Bayes rule to kind of convert every term into a node given its parents only, okay. That's what we did, and we have tables for that, so we can actually we know, so this conditional probability, just we can compute that actually. For W is equal to 0, you can just look at W is equal to 0, what all terms are involved, these are the terms involved, and W is equal to 1, these are the terms involved, okay. So once you know this conditional probability of W given F is equal to something and C is equal to something, this conditional probability is a binary random variable with certain biases, right. Just these two evaluate to some value 0.17, 0.82. You flip a coin according to that. That's going to be the realization of the random variable given these other random variables, given its Markov blanket related variables, okay. Just recall why we're doing all this, because Gibbs sampling needs these conditional probabilities, okay, to sample from the whole distribution. The whole distribution had 9 random variables, right, but Gibbs sampling will do it part by part if it has access to these types of conditional probabilities, okay. Same thing, I mean, I think second example I'll skip because I am running out of time. So this is an example where I'm trying to find the conditional probability of C given its Markov blanket. Its Markov blanket, this example has, as you know, I mean, here there's a couple of children, couple of parents of those children, and its own parent. Okay, so all those have to be involved in the computation of getting a sample of C given its Markov blanket. Okay, so that's fine. Yeah, so there's a bunch of computations related to that, and okay, actually. Yeah, and why did I say we only care about Markov blanket is written in a more mathematical notation here, is because there's some normalization constant that drops all the other variables. Okay, there's some additional variable products that come here and in the normalization, so they both cancel, and so you only care about things in the Markov blanket. Okay, so this slide is just saying that. That's fine. So now what we're going to do in the next 10 minutes is to understand how why does Gibbs sampling work. Okay, so I don't know if I had a, so just to I don't know if I had an explicit slide on this. Gibbs sampling, as I said, I want to get a sample, I want to get samples from P of x. Okay, so x is let's think of x being x1, x2 and x3. Okay, as said, start with some little x 0. Okay, that's some value, let's say 1, 2 and minus 1. Start with some initial sample. Then what you do is get a sample which is going to be, I'm going to now start filling the first samples first coordinate is the probability of x1 is equal to whatever little x given x2 is equal to 2 and x3 is equal to minus 1. Okay, so where did I get 2 and minus 1? From the previous sample. Okay, so this is how I generate the first coordinate of the next sample. So this is my sample table, let's say it's called x0, x1. I had 1, 2 and minus 1 already, and I'm now telling you what's the number for the next sample. Okay, clearly x1's first coordinate depends on what were the values in the previous previous vector, 3-dimensional vector. Then I'll do x2 of the first sample as the probability of x2 is equal to some x given x1 is x1, let's say, realized to be 5. Okay, so that's, let's say this is 5, then x1 is 5 and x3 is still the old value minus 1 from the previous example. Similarly, x3 is probability of same thing given x1 is 5 and x2, let's say x2 realized to be 0. Okay, then x2 is 0. Okay, so you get x3 is equal to something. Okay, maybe x3 is 2, then you put the 2 there. Okay, so that's how you fill the next example, and then you keep repeating this. So next you again pick the first coordinate, and for that you needed these conditional probabilities, and that's why we went through that Markov blanket exercise. Okay, for directed probabilistic graphical models, but in general you need to have access to this. Okay, so this is Gibbs sampling, and the question is why does me generating samples like this, sorry, x superscript 0, x superscript 1, superscript 2, why do these samples look or are actually as if they are coming from P of x? Because I'm not explicitly sampling from P of x, I'm only sampling from these conditional probabilities. So there's a gap, right? Why is me sampling from conditional probabilities coordinate by coordinate giving me samples from the joint distribution? Okay, and the idea behind that is through the lens of Markov chain. Okay, this Markov chain idea. Okay, which means that there is some Markov chain. I'm going to describe what a Markov chain is. Okay, that leads to us, even though we are doing these coordinate wise steps, it leads to us getting samples from the distribution that we care about, which is this guy. Okay, sorry, it's not. Yeah, any questions about the goal? Okay, so what is the as I said, we want to find sample from P of x. Okay, and the idea, the Markov chain idea, is to somehow come up with a transition probability distribution. Okay, a transition probability distribution whose stationary distribution is going to be the distribution that we care about. What do I mean by that? Okay, for that I think let me just use this. Okay, so what is the Markov chain? Okay, Markov chain is nothing but a sequence of random variables. Okay, a sequence of random variables. So think of and it can be represented using what is called a queue of what is called a transition probability matrix. Let's say the random variables are taking some finite values. So yeah, let's say they're taking finite values, then x to x prime. Let's say. So q of x to x prime is called a transition probability matrix. So let's say my sequence of random variables, let's call it x1, x2, all the way to x. I mean all the way to infinity. But let's say this is a sequence of random variables, a lot of random variables. I can say how these random variables, what is the distribution of these random variables by just describing what is called the transition probability matrix and the initial random variables distribution. Okay. What do I mean by that? So here's a picture. So let's say all these random variables are binary random variables. Okay, they only take two values. Okay, so which means that x1 is binary, x2 is binary. So let's say they only take values a and b. Okay, all of them take value a and b. Okay, then this q is a table which is like this. So a to a, b to a, and b to b. So q is essentially a table which says if my current random variable, I mean the current doesn't like let's say xt, so x1 it has a value of a, what is the probability that x2 is going to take a value a or b? Okay, maybe given this is a, it takes a value a with probability 0.5, b with probability 0.5. Okay, but if x1 is b, then x2 will take a value a with probability 0.7 and take a value b with 0.3. So this is a table which says given the previous random variable, what's the probability with which the next random variable realizes. Okay, that's essentially what a Markov chain is. If these are called states or whatever, if these are just two, then this is a table of size 2 cross 2. If it takes 10 different values, each random variable takes 10 different values, and it's going to be 10 cross 10. And of course rows have to sum to 1 because given it's like a conditional probability. Each row is a conditional probability. Condition on the previous random variable, what's the next random variable going to take. Okay, that's what each row is. Okay, so that's a Markov chain, and Markov chains have some interesting properties under some nice conditions which I'm not going to go into the details. There's going to be what is called a stationary distribution. Okay, stationary distribution pi. So it's a distribution. For us, any random variable only takes two values, so it's a distribution over two values. Okay, there's going to be a stationary distribution. It's going to be a distribution such that this property holds. Okay, this property holds, which is pi of x prime is going to be equal to pi of x times q of x to x prime. So let me explain this properly. So the one on the right side, okay, is basically saying, let's say you're in some state x, okay, a or b. So let's say think of the summation as just sum over a or b. Okay, you being in a with some probability pi, so pi of a times you transitioning to x prime. Let's pick x prime to be a, a. Okay, so let's say x prime is a. Okay, I'm saying that a stationary distribution is such that you being in some state, let's say a, and transitioning to this target state a, plus you being in state b and transitioning to target state a, that summation, the summation should be equal to the probability of being in the target state a. Okay, so I guess in the previous example, all I'm saying is pi of a should be equal to pi of a times q of being in a and going to a plus pi of b times q of being in b and going to a. Okay, so I guess intuitively what is this saying is that you told me some q, it's a matrix essentially. I'm writing a bunch of linear equations for the matrix, right? These are the entries of the matrix, right? Bunch of equations. So pi is a variable. It's like x is equal to ax is equal to x. Basically, that's what this is. So it's something like a pi is equal to pi. Some equation like this. Okay. So pi which satisfies a pi is equal to pi is called a stationary distribution. Okay. I'm simplifying a lot of things very informally, but this is what the stationary distribution is, and this is the equation, and this is what I wrote in general. Okay, so that's called a stationary distribution. Now we want to sample from P of x. What we're going to do is construct this object, this transition probability object, okay, such that this transition probability object stationary distribution is P of x. Okay, so P of x is what we care about. We'll construct this Q of x to x prime, this transition thingy, such that it describes the Markov chain, of course, such that its stationary distribution is P of x. Okay, which means that if I start from some x naught, okay, it describes the Markov chain, so I can start from some starting realization. I look at the transition probability matrix. I can sample the next guy because Q is telling me what is a given x, what is the probability of getting x prime some value. Okay, so I can sample from Q, keep going forward in the chain, and those samples are as if they come from the stationary distribution eventually. Okay, that's the whole idea of stationary distribution. And since our stationary distribution is the target distribution, we're getting samples from the target distribution after some burn-in or some initial amount of time. Okay, so that's the very high level idea of what a Markov chain based sampling technique is. The samples are going to be correlated, but there's going to be an explicit or implicit Markov chain object, this transition probability matrix or function defined, whose stationary distribution happens to be the distribution from which we care about getting samples from. Okay, and if we keep running the chain, as in we keep sampling from Q, we get samples from P eventually. Okay, because of the stationary distribution business. Any questions? No? Okay. So that's the general idea. I mean, so we haven't talked about Gibbs sampling yet. Now Gibbs sampling implements a specific Q function, okay, specific transition probability function, which we saw in this slide here, right? It says given previous x, it tells me what the next x is, but every coordinate wise. So it given the previous x, it will tell me, or given the previous, in this case previous two numbers, it's telling me what the next number is, and 0 if you tell me these two numbers, and so on, right? So there is some dependency. There is a chain type of a dependency that Gibbs sampling is doing. Okay, and of course it's using these conditional probabilities, which are related to the target distribution. So it's defining a Q which is related to the target distribution. Target distribution P of x is relating a Q, so it's defining a Q whose coordinate wise things are related to the final distribution. So of course if this, it's intuitively kind of makes sense that maybe if this Q is nice, then you are actually getting samples from the target distribution. Okay, so there is no ambiguity here, so because the Q is defined in terms of these things related to the target distribution, right? So we have to now, so what is left is to show that Gibbs sampling has a stationary distribution which is actually P of x. Okay, so what are we going to do? We know that Gibbs sampling uses these guys, P of x1 given everything else, P of x2 given everything else, P of x3 given everything else. That defines some Q. Okay, we're going to say that, okay, if that is the Q, that Q has a target distribution or has a stationary distribution which is actually P of x. Okay, how do we show this? Okay, that's what we're going to spend the next couple of slides on. Okay, and we're not going to really show it directly. We're going to use an important fact to show that Gibbs sampling's target is, stationary distribution is P of x. Okay, and that fact is let's skip this slide, too much text. Okay, okay, whatever I said is essentially this stationary distribution idea here. So the fact is detailed balance equation. Okay, what do I mean by that? So if pi is a stationary distribution, so we said what a stationary distribution is, a pi is equal to pi or something like that, right? If pi is a stationary distribution, then pi of x times the probability, so probability of me being in a taking a value for a random variable at, let's say, current time, and me going from that random variable value to another random variable value x prime is the same as me being in the probability with which I'm at the second random variable value, okay, and transitioning from that value to the current value. So all I'm saying is, me being in some state, I'm using state, but like some value, me being, like it's like saying pi of a, me taking the probability, me having a probability. So pi is a stationary distribution. It's a distribution over a comma b, for example, in my running example. So let's say detailed balance, all is saying is pi of a times probability of going from a to something else, let's say b, is the same as me being in state b and times probability of me going from b to a. Okay, so where am I getting probability of a to b and b to a? That I'm getting from the table, right? Given b, what is the probability of me going to a? It's from that matrix. Okay, so that's called a detailed balance equation. Okay, so detailed balance, so this equation implies stationarity in the sense that if you have detailed balance, if this equation holds, star equation holds, implies that pi is a stationary distribution. Okay, if there is a pi which satisfies the detailed balance, it implies pi is a stationary distribution. Okay, and that's easy to see because you can just sum up the left hand side of the detailed balance equation, okay, over all x. That's going to be the same thing right hand side with sum over all x, but that, the first pi doesn't depend on x, so you just use pi of x prime and push the summation inside. Summation inside sum over all x of the transition from x prime to x is 1. Okay, because it's a conditional probability distribution, sum over all the arguments on the left hand side is 1. Okay, so which means that this is equal to left hand side equal to right hand side, and that was the definition of the stationary distribution. Remember, this left hand side equal to right hand side is just a pi is equal to pi. We just saw this definition before. Okay, so detailed balance implies stationary distribution. Pi is a stationary distribution. Now what we're going to do is show that the Gibbs sampling's conditional probabilities satisfy the detailed balance equation. Okay, so let's do that. Yeah, so this is the, I guess, last slide before you guys like really fall off the cliff. So what is the transition probability, right? So for Gibbs sampling, probability of going from a sample x, from a sample, let's say time t to time t plus 1, let's say, is the probability of me having this pair where I isolate the ith coordinate. So same x, I just broke it into two parts, x and x bar of xi and x bar of I is just that together form x. Okay, because I only update one variable at a time, I'm only changing xi to xi prime. Okay, the remaining part of that variable is the same. Okay, that's one step of the Gibbs sampling. Okay, I'm going to show that satisfies the detailed balance equation. Okay, so we're going to call this probability of x prime given everything else. Now left hand side is the left hand side of the detailed balance equation. So pi of x times pi of x times q of x to x prime is the probability of x times probability of x prime, this guy over here, this whole thing here, given other coordinates. Okay, so we only care about the ith guy getting updated. Okay, that's the step that happened in the that's the one step that happened in Gibbs sampling. Now that is equal to, so here the next equality is just x is actually just xi and everything else. Okay, that's the equality, first equality. In the second equation, we are writing this joint distribution of xi and everything else as xi given everything else times everything else. Okay, so it's just the joint distribution is just a product of conditional probability times remaining guys, right? So that's the second inequality here, this one, let's call it second inequality. Okay, times the previous term that was already there, that's this term. Okay, now what we'll do is we'll merge these two, I guess, the bold face underlined term, which is probability of x bar times probability of x prime given x bar. Okay, that is nothing but the joint distribution between x prime and x bar. Okay, that's this time, that's the third inequality here. Okay, and that third inequality, just writing in terms of q and pi, is just first term is q and the next term is pi. Okay, So anyway, so I think we can discuss offline if you're not following this, but it's just that Gibbs sampling update somehow ensures detailed balance is true, and we just saw in the previous slide that if detailed balance is true, then pi is the stationary distribution. Okay, and here we used the p of x as the p of x as part of instead of pi here we substituted p of x. This is p of x. Okay, so p of x is pi and it is a stationary distribution. Therefore, Gibbs sampling works. Okay, that's the goal. Now let's skip performance issues. Okay, and so that's Gibbs sampling, but that's just one element or one function, one procedure in the MCMC techniques. Okay, there are many techniques being invented, even currently in research, and there is a whole family of techniques. So one other family of techniques that you should go read it offline is Metropolis Hastings. Okay, so Metropolis Hastings family of techniques combines this accept reject idea from rejection sampling. Okay, and this Markov chain part where you depend on the previous sample to get the next sample. Okay, so there is a Markov chain, there is a different Q function just like Gibbs sampling, but it also combines the idea of accept reject from the rejection sampling idea. Okay, and I'll not go into the details of the algorithm because it's pretty straightforward what the accept reject step is. Okay, and how to sample from given the previous sample, how to get the next sample. So it's not terribly difficult. It's it's simpler than Gibbs sampling actually. So model of that. Any questions about sampling, Gibbs sampling, or the previous rejection sampling, or importance sampling and Monte Carlo averaging? Is it too much? I think we compressed, but we looked at only two techniques, right? I mean, Gibbs sampling was the major thing. We wanted to understand why Gibbs sampling works. Okay, you can always call Gibbs sampling function call in any of the like pi MC3, but you need to know why it's called Markov chain and why Gibbs sampling works. Okay, so anyway, in summary for today, we just looked at inference. What is inference? What is a way to do inference exactly? Variable elimination and belief propagation. And then the third thing was approximate methods. We saw Monte Carlo averaging, importance sampling, rejection sampling, and Gibbs sampling. Okay.